video, we'll be discussing some of the sections of Chapter 13 that talk about solutions, specifically sections 13.6 through 13.8. And this section talk about molarity and some other stuff that we're going to see in a few minutes. So, by the end of this video, you will be able to calculate molarity. Also, you will be able to use molarity in calculations. You will calculate solution dilution, and also you will use solution stoichiometry. So first we're going to talk a little bit about the molarity. Molarity is defined as the number of moles of solid per liter of solution. Molarity is the unit of concentration. It's a unit of concentration. There are few other units, but this one is the most common actually when you are preparing solutions. Okay, the molarity. And a solution, it's at least composed of two components. One is known as the solvent, and the other one is known as the solid. The solvent basically is normally the component present in the greatest amount, and all the others components are called solutes. Okay, so at least if you had just one, it's going to call solid, but you can have more than one in a solution. So you have, for example, you can have a solution of glucose and sodium chloride in water. Water is the solvent, and the solid will be sodium chloride and glucose. Okay, so you can have more than one solid, but most of the time, for our type of problems that we're going to cover during this chapter, is going to be just one type of solid. Okay, so the molarity, first of all, is expressed or defined as an capital M, and this is equal to the moles of the solid divided by the liters of solution. Know that the molarity is moles of solid per liters of solution, not per liter of the solvent. To make a solution of a specified molarity, you usually put the solid into a flask and then add water to the desired volume of solution. So for example, here we want to prepare a solution of sodium chloride with a molarity of 1.00. So uh, when we have 1 mole of sodium chloride is equal to 58.44 grams of sodium chloride. So to a flask, that most of the time when we are preparing solutions, we use a volumetric flask. This volumetric flask is specific for one amount of volume. Okay, so this one, for example, is going to be 1 liter, but you can have volumetric flask for 100 milliliters, for 2,000 liters. So, but it's specific for just one volume. Okay, so you can't measure here, for example, 500 milliliters. Okay, this volumetric flask is just to measure 1 liter of solution. So the first thing that you're going to do is to add the solid. In this case, is sodium chloride in the flask, and then you're going to add enough water to dissolve the sodium chloride. And then you're going to keep adding water until you reach this mark. When you reach this mark, you have 1 liter, the volume of 1 liter, as we can see here. And here we have a solution of 1 molar of sodium chloride solution. Okay, so first of all, you're going to add the solid, then you're going to add water enough to dissolve, and once it's dissolved, then you complete until the mark with more of the solvent, that in this case is water. So let's do an example of how to calculate the molarity of a solution. In this case, we're going to do it by adding 50.5 grams of sodium chloride into a beaker, and we're going to add water, okay, to make a 1.5 liters of sodium solution. So by looking at this, as I mentioned before, most of the time the solvent in our during this class is going to be just water. Okay, so you can identify which one is the solvent, and the solid will be sodium chloride. So if we want to determine the molarity is equal to what? To moles of the solid divided by the liters of the solution. Do we have some of this information here in the problem? At least we have direct the liters of solution, 1.50 liters. So this is this part, okay? And then we need to look for the moles of the solid, but we have what? We have the mass of the solid. So we need to change mass to moles. And how can we do that? How can you change the unit of grams to the unit of moles? using the molar mass. Okay, so here we have the mass of sodium chloride. This is the inverse of the molar mass because we want to cancel the grams of sodium chloride. And by dividing 50.5 through to 58.44, we're going to have the moles of sodium chloride, the moles of the solid. Okay, so these are moles of solid, and we have the liters of solution. So now we just substitute these values here. Molarity, okay, 0.2652 divided by 1.50 liters of solution, and this will be the molarity. Now, I want to let you know that this equation here has three variables. You have molarity is one of the variables, the other one is the moles of the solid, and the other one is the liters of solution. You just need two of the three variables to determine the third one. So with this formula, you can determine the molarity, but also you can determine the moles of the solid if you have the molarity and the liters. Or if you have the moles and the molarity, you can determine the volume of the solution. Okay, so this equation could help you to determine not just molarity, but could help you to determine the volume of the solution and also the moles of the solid that eventually you can change moles to grams by using the molar mass of whatever solid you have. Okay, so that's really, really important. So this is not just to determine the molarity. You can determine the volume of the solution or also the mass or the moles of the solid and then the mass by using the molar mass of whatever solid you have. Okay. So let's see another one. Determine how many grams of sucrose are contained in 1.72 liters of 0.758 molarity of sucrose solution. So now you have molarity and now you have volume. So you have molarity and volume. So how can you determine the moles of the solid? By doing what? By multiplying the molarity times the liters, that will be equal to the moles of the solid. Okay? And once you have the moles of the solid, then you can obtain the grams by using what? The molar mass of the glucose. Okay, so basically, you by using the molarity, you can change the liters to the moles, and then use the molar mass of sucrose to obtain the mass of the sucrose. Okay, so here, as I mentioned before, this one will be equal to the moles, basically, when you multiply the molarity times the liters, and then the moles you multiply also by the molar mass of the sucrose, and you will obtain the mass of sucrose. So the volume times the molarity. Okay, 0.758. Remember, molarity is equals to the moles of the solid divided by the liters of solution. So that's why we change here the molarity to the expression of the two units. Okay, because molarity has two units: moles of glucose and sucrose, sorry, and liters of solution. So in that way, we can cancel the liters of solution from here, and now we have the moles. And then by multiplying to the molar mass of sucrose, we can cancel the moles of sucrose, and we will have the mass of the sucrose that we need to add, uh, so we can have a solution of 0.758 molarity of sucrose solution. Now let's talk about what happened when we have a solution with, instead of a molecular solution, an ionic solution. The reported concentration of a solution containing a molecular compound usually reflects the concentration of the solid as it actually exists in solution. So, for example, 1 molar glucose solution contains 1 mole of glucose per liter of solution. The reported concentration of a solution containing an ionic compound reflects the concentration of the solid before it is dissolved in solution. Why? Remember that we mentioned in class before that when you dissolve an ionic compound, you're not just dissolving it. Also, you are doing what? A dissociation. So instead of one, if you can see, for example, particles, if you add sodium chloride, that is an ionic compound, you're adding just one particle, sodium chloride. You are adding that molecule to the water. But when it gets to the water, it's dissociated in two particles because you're going to have now the ion of sodium and the ion of chlorine. You don't that doesn't happen with the glucose because glucose is a molecular compound. So when you add one particle that is a glucose molecule to water, you still have the dissolve in solution a molecule of glucose. But when you add an ionic compound, as for example sodium chloride, you don't have anymore like the combination of those ions. They are dissociated, they're separated in water. So instead of one particle, now you have two. And that will affect eventually the concentration because when we have, for example, a solution of 1 molar of calcium chloride, that solution contains 1 mole of calcium per liter and 2 moles of chlorine per liter. Okay, because this is dissociated. And instead of now of one particle, we're going to have three: 1 mole of calcium and 2 mole of chlorine. The concentration of the individual ions present in a solution containing an ionic compound can be approximated from the overall concentration. This approximation because when an ionic these are approximations, sorry, because when an ionic compound is solved in solution, some of the cations and anions may pair up so that the actual concentration of ions are lower than what you would expect if you assume complete dissociation occurred. So let's see an example to help you maybe understand a little bit more this concept. Determine the molar concentration of sodium ions and phosphate ions in a 1.50 molarity sodium phosphate solution. So what we have is the concentration of the sodium phosphate, 1.50 molarity. And we want to determine the molarity of sodium and the molarity of uh, phosphate. What happened? The molarity of sodium, how many sodiums we have here? We have 3. So that's why we multiply that times 1.50, and this is the molarity of the ions of sodium in the solution. It's not 150, it's 4.5 because we have 3 particles when it dissociated. If this could keep together in solution, then we can't talk about the molar concentration of sodium and phosphate. But because it's an ionic compound, they will dissociate it, they will separate in 4 particles instead of 1. We're going to have 3 sodium and 1 phosphate. And for the concentration of each, we're going to have a concentration of sodium and a concentration of phosphate. The concentration of phosphate, we just have 1 phosphate. So that's is the same concentration of the compound per se. So that's why it's 1.50 molarity. But because sodium, you have 3 of them, it's going to be 3 times that concentration. Okay, and that will be the concentration for ionic compounds. Let's talk now about solution dilution. Solutions are often stored in concentration forms called stock solutions. And maybe you will see this when you go to Starbucks and you ask for uh, this kind of tea that they have there in jars, and then they add it to the cup and then they add water. That first solution that was in that jar, that is a stock solution. And most of this time is really, really concentrated. Okay? Many lab procedures call for less concentrated solutions, so chemists must dilute the stock solution to the required concentration. This is done by combining a certain amount of the stock solution with water. To determine how much of the stock solution to use the dilution equation, that is M1V1 equals to M2V2. Also, sometimes you're going to see instead of a 1 an I, and instead of a 2 an F. That will be M initial, volume initial, molarity final, and volume final. Okay, so this will be the initial and this will be the final. Once again, here we have how many variables in that equation? We have 4 variables. We have the initial concentration. This is molarity. Molarity is concentration. We have the initial concentration. We have the initial volume. We have the final concentration, and we have the final volume. So if we have 3 of any of these variables, we can determine the fourth. Okay? If we have the initial concentration and we have the final concentration and the final volume, we can determine the initial volume. If we have the initial volume and the initial concentration and the final concentration, we can determine the final volume. If we have the final volume, initial volume, an initial concentration, we can determine the final concentration. So it's really important to understand that this equation could help us to solve four different type of problems. If we need the initial concentration, we need to look for this one, and we need to have the other threes. If we're looking for the initial volume, we're gonna use this equation by rearrange this equation so we can have the equation that V1 is equal to M2V2 over M1. And if we have to determine the final concentration, then it will be M1 V1 over V2 that we need to rearrange so we can define which one is the equation that we need. So M1 and V1 are the molarity and volume of the initial concentrated solution, and M2 V2 are the molarity and volume of the final diluted solution. Now, this equation works because the molarity multiplied by the volume gives the number of moles. Okay, remember that molarity is moles over volume. So if we multiply volume to volume, we cancel the units of volume and we're going to have moles, which is the same in both solutions. So the number of moles is the same in the concentrated or in the diluted solution. The equation M1V1 equals to M2V2 applies only to solution dilution, not to stoichiometry. Okay, so this is really important. We're going to use this when we're going to talk about dilutions. M1V1 equals to M2V2. One of the most common solutions that we need to dissolve in a lab is acid. When diluting acids, always add the concentrated acid to water. Never add water to concentrated acid solutions. Okay, so always add first the concentrated acid to water. Now let's see the following problem. Prepare a 5 liter of a 1.50 molarity potassium chloride solution from a 12.0 molarity stock solution. We need to identify what we have. We have here volume, we have here concentration, and we have here concentration. So we need to look for volume. By using the dilution equation, okay, we have one volume here, we have one concentration here, and we have another concentration here. Now, which volume do we need, the initial or the final? Here it says prepare a 5.0 liter. So at the end, what I'm going to have is a volume of 5 liters. So this is the final volume. So this is the final concentration. And this is the initial concentration. So we need to look for the initial volume. Okay. So here we have the equation, the dilution equation. We have the initial concentration or molarity, that is 12.0 molarity, the final concentration, that is 1.50 molarity, and the final volume, that is 5.00 liters. Once again, prepare this. So at the end, you're going to have this. So that's why these are the final, the number 2. And from this, so we're going to prepare this from this one. We have this at the beginning. So this is the initial concentration. So we need to look or to find the um, initial volume. So by rearrange the equation of M1V1, we want this rearranged by itself. So we divide alone, we divide M1 in both sides, and we're going to have here M2V2 is divided by M1, it will be equal to the volume. So the initial concentration, that is 1.50, times the final concentration, that is 1.50, times the final volume, that is 5 liters, divided by the initial concentration. This is gonna we're gonna obtain here the volume, okay, that we need from the initial or the stock solution. So from this 12 molarity, we need to obtain a sample of 625 milliliters. Okay, so in other words, here we have the volumetric flask. Okay, this one is for 5 liters. We're gonna add 6.625 liters, that is 625 milliliters of the solution of 12.0 molarity stock. Okay, and then we're gonna add water enough to reach the mark, okay, of a volume for a total volume of 5.00 liters. And this is the diluted solution from prepared prepared from the stock solution. That is the yellow one that was 12 concentration of 12.0 molarity. Remember this equation M1V1 is equal to M2V2. You can use it in 4 different scenarios to determine the initial concentration or to determine the initial volume or the final volume or the final concentration. Solution stoichiometry. In reactions involving aqueous reactants and products, it is often convenient to specify the amount of reactants or products in terms of their volume and concentration. We can use the volume and concentration to calculate the number of moles of reactants or products, and then use the stoichiometry coefficients to convert to other quantities in the reaction. So, in other words, as we saw before, we can use this map, okay, solution, a general solution map. We start with the volume of A, one compound, and then we need to change this to moles. Volume, liters, moles. So what do we need here to change for volume to moles? What conversion factor can we use here? That conversion factor is the molarity. Okay, because the molarity, remember that is mole over liter over volume. Okay, so if we need to turn from volumes to moles, we need to use the molarity. Then once we have the moles of A, we need to obtain the moles of B. So what should we use here to go from moles of A to moles of B? A conversion factor that are this are coefficients of the balanced chemical equation. And then we can obtain the volume that we need of the other compound by starting with the moles using again the molarity of the B compound. Here we're going to use the molarity concentration of A and here the concentration of B. And here the coefficients obtained from the chemical equation, balanced chemical equation. Here we have A and B. There are 2 different substances involved in the reaction, and the conversion factor between them comes from the stoichiometric coefficient in the balanced chemical equation. This one here is from those, and to this conversion factor and this one are the molarity of A and the molarity of B. So here we have an example of this is a neutralization reaction. By the way, we have sulfuric acid, sodium hydroxide, the combination of these two. This one is the acid, this one is the base. You're going to produce a salt and water. Okay, salt is sodium sulfate and water. So this is a neutralization reaction where an acid and a base will produce a salt and water. Now, the question is, how much of 0.125 molarity of sodium hydroxide solution do we need to completely neutralize 0.225 liters of a sample of 0.175 molarity of sulfuric acid? So here we have the initial volume. Okay, the volume that we have here is of sulfuric acid. So we can go from the volume of sulfuric acid to moles of sulfuric acid, okay, by using the molarity, because remember that in molarity we have moles over volume. So by using these two, we can obtain the moles of the sulfuric acid, and then we need to change from moles of sulfuric acid to moles of sodium hydroxide. Okay, and this moles of sodium hydroxide, we can do that by using the coefficients of the equation. Okay, and then we can turn from those moles to the volume because they are asking how much solution. How much solution, that means how much volume we need, okay, to create this. So in other words, here we go. We have the volume of the sulfuric acid. We can change that volume to moles by using the molarity, and then moles to sulfuric acid to moles of sodium hydroxide by using the coefficients of the equation, and finally the moles of sodium hydroxide to liters of solution by using the concentration of sodium hydroxide. Okay, so here we have all that information. This one is the molarity, okay, for sulfuric acid. So once we do this multiplication here, we're going to have the moles of sulfuric acid. Then the ratio, okay, from the equation, 2 moles of sodium hydroxide, 1 mole of sulfuric acid. When we multiply this, we're going to have the moles of sodium hydroxide, and then we can divide by the concentration of sodium hydroxide to obtain the volume of that solution. So basically here we can do all the mathematical operation, and at the end we're going to have the volume that we're going to need, okay, to react with this volume of sulfuric acid. Okay, so this is the volume that is going to react with this volume of sulfuric acid. So the sections, basically we talk about solution concentration. One common way to express solution concentration is the molarity. We also talk about the solution dilution. And these problems are most convenient solved using the following equation. M1 V1 equals to M2 B2. Initial volume and initial concentration equals to the final concentration and the final volume. And this will be all for this sections, okay, for chapter 13, sections 13.6 through 13.8.